Hi, my name is Peter Wolf, and I will talk to you about developing complex and frequency stabilized laser sources for LISA ground tests carried out at Syrte at the Paris Observatory by a group of people mainly driven by Wally Acef, who's been working on iodine lasers for quite a while, iodine stabilized lasers, with financing from a number of partners, and in particular the French space agency CNES, and a number of industrial partners like Kilia or Sodern. French activities in LISA are mainly data processing and assembly integration, verification and testing of the payloads, the moving optical subassemblies in particular. It's carried out by a number of partners, laboratories, industrial partners, under the driving forces of CNES, the French space agency. So as I already said, with the Syrte we develop the laser sources for the AIVT activity and do quite some data processing as well, but that's a different story and is part of a different talk at the LISA symposium. Essentially, in terms of the laser sources, we are at the moment developing two laser sources called Silex V1 and V2. Silex stands for Syrte LISA laser experiment. Silex V1 is in fact already delivered, and Silex V2 is under development at the moment, and I'll tell you more about that in a minute. In the long run, we will need about 6 such laser sources to be used in the integration of the different flight models that have to be carried out in parallel, as well as the engineering and qualification models of the MOSAs. All requirements for those laser sources are the same as those for the flight sources, so maybe with a bit more versatility, and I will talk about that as well. So here is an overview of the laser sources as we develop them at the moment. So this part here called V1 is already available and delivered. It's essentially 2 lasers, one master and one slave, locked to each other with frequency offsets or frequency drifts between them that can be programmed, and power stabilized using 2 AOMs that deliver the signals needed for the interferometry or for the MOSAs or for the testing. Currently we are developing the V2 part, which is a frequency tripled iodine stabilized telecom laser that will meet the absolute frequency stability requirements of 30 Hz per square root of Hertz, and that will be frequency locked to the doubled master laser, or the other way around, rather the master laser will be frequency locked to this source, thus conferring that stability to all of the laser signals delivered to the interferometry. So like I said, the frequency difference between these 2 lasers can be tuned within the heterodyne frequency band of the LISA beat nodes, so something like a megahertz to 50 megahertz, and we can apply frequency drifts or chirps or any indeed frequency modulation, even if we want to simulate Dopplers or things like that, up to, well, we've gone up to 10 kilohertz per second, but we can go further if required. So here is the V1 frequency source, so Silex V1 in more detail. I won't walk you through all of it, but essentially there's 2 lasers here, 1064, both of them power stabilized using an AOM and a power pickup here and here. And then the beat node between the 2 is used to lock the slave laser onto the master laser with a tunable frequency difference, which is in the megahertz range as required for LISA. In the end, they deliver about 1 milliwatt each to the interferometer benches that require the signals. There's also about 100 milliwatt goes into a dump at the moment. This will be used to lock them to the iodine stabilized source of the Silex V2 bench. Maybe the only important thing to say here is that all control signals, whether they are measured on site or whether they are used for power or frequency control, can be replaced by signals from external sources, for example from phase meters on the interferometer bench. So it's versatile in the sense that we can interface with the interferometer bench if required. So this is what it looks like. It's overall about 130 centimeters in height. It's still quite a laboratory setup, as you can tell, mainly because we built it from material that was still around in our laboratory, in particular the two lasers, a fiber laser here and the YAG laser, which is here, plus its control electronics here. But it's movable, it's on wheels and easily transportable, and especially important is the fact that it's all fibered, everything is fibered, so there's no alignments required once it arrives wherever you want to use it. What is new is what's inside this box up here. It's two levels, one contains the AOMs for the power control, plus associated fibering, etc., and the other one contains all the diodes and associated electronics. And here is some of the performance. So this is the frequency stability of the two output lasers, one with respect to the other. What you see is essentially the phase noise of the phase-locked loop, well below the LISA requirements, of course. In terms of intensity noise, maybe the most important region is where at 1F and 2F, where F is the heterodyne frequency of LISA, so that's in the sort of 5 to 50 megahertz band. As you can see, that's about a 10 to the minus 7 per square root of hertz. In fact, that is the noise of the diode we used to do this measurement. Even with no light on it at all, it still has the same noise. And the laser noise from other measurements in other labs, we expect it to be more around 10 to the minus 8. But anyway, it demonstrates that our power or frequency stabilization systems do not add any frequency noise in the LISA heterodyne frequency band. Okay, I will now come to the Silex V2, which is the iodine stabilized part. So as I already mentioned, we start from a telecom laser at 1596 nanometers, which we frequency triple, which gives us 532. And then that is locked to the doubled laser from the V1, so the doubled 1064, which locks essentially the 1064 laser to the iodine and thus confers it its stability. At the moment, we already have two such setups at 1542 and 1544. Of course, that does not give you quite the correct frequency for LISA, so we're now building a third one, which is intended for LISA, and we of course think its frequency stability will be significantly better than 30 Hz per square root of hertz. The delivery of this is planned in the fourth quarter, well, towards the end of 2021. This part will be very small, about 10 liters in volume, low mass and low power consumptions, about 20 watt. Again, fully fibered and robust. The point is that this is developed also for other applications that require frequency stabilized telecom lasers or their double or triple frequencies on ground or in space. So let me first say a few words about the existing setups. So we have two of them, in fact, 1542 and 1544 nanometers. The basic idea, so this is the tripling part. We start from the laser, then we have a second harmonic generator, nonlinear crystal, and a some frequency generating nonlinear crystal, which in the end gives you the 3 times the frequency of the input laser. This is the photo of the whole thing. This includes everything, so once it's open you have the lasers and amplifiers here, or the fibered components including the 2 crystals which are here. This is a zoom on the crystal, so this is the doubling crystal, which is fully fibered, and this is the tripling crystal where the inputs are fibered. The output in this version is free space. In the version for LISA, that will be fibered as well. So here you can see the output actually here of the green light, and maybe the take-home message here mainly is two messages. One, that we get a typical tripling efficiency of about 36% of the input light for a total power consumption of about 20 watts. And this has been in continuous operation since July 2014, so it's very robust and easy to use, and works pretty well. You can find all details in this article if you're interested more in this tripling part. Let's now look at the iodine stabilized part. So we have two iodine cells we use at the moment. One is a room temperature cell, which is inside the magnetic shield, which is here. And the other one is a cooled iodine cell at minus 11 degrees Celsius, which has no magnetic shield. In the background you can see actually the tripled laser. And this is the performance in terms of frequency stability. For the cooled cell, the high frequency region is very good and well below LISA specs. However, at low frequency, because of the strongly perturbed magnetic environment at the Paris Observatory, thanks to the Paris Metro, essentially, leads to low frequency drifts and variations that we do not have when we put on the magnetic shield here on the room temperature cell. So in room temperature, the high frequency performance is less good, but you see we keep the LISA specs down to something like a few millihertz in Fourier frequencies, which is within the specs required for LISA. So that was the existing setup. Let us now turn to what we are developing for LISA. So again, this box is pretty much the same as you've already seen. It's a little different as it's not at the same wavelength. Also, we have rearranged the amplifiers and the crystals, but the principle is pretty much the same. It includes the EOMs, two EOMs for power control, and then delivers the two 532 nanometer signals for the pump and the probe beam to the iodine cell. As optional outputs, we have the 1596 nanometers or the doubled frequency, so 700 or something nanometers if required. The iodine cell, this is a photo of the actual cell that is being used. It's a 15 centimeter square cell with multiple passages, as you can see. It sits in this housing with a monolithic optical bench up front, which includes the two fiber couplers here and here that come from the red box, and all the beam splitters, combiners, polarization control, the diodes, and it's all monolithic, so there's no movable parts, and although it's free space, there will be no alignments required once all this is set up. To finish, I will say a few words about the setup we have at Syrte for the infrastructure we have at Syrte for developing such lasers. So we have a number of atomic clocks and ultra-stable oscillators, be it in the microwave domain. So this is a cryogenic sapphire oscillator, for example, with very good short-term stability. We have hydrogen masers, we have cesium or rubidium fountains. And in the optical lab, we have strontium clocks. We have a mercury clock, which is actually not here, but which also runs in the optical domain. And we have by now 4 ultra-stable cavities that are used to stabilize lasers. Everything is linked via this frequency comb, the RF, as well as the optical signals, which can deliver at the moment 1542 and 1544 nanometer light to the Iodine lab about 200 meters away through a fiber link, which we can compensate for its phase fluctuations well below the performance required for LISA. And we can also, of course, extract 1064 from the frequency comb and deliver it to the Iodine lab, with all these signals having stabilities which are well below the requirements for LISA. So we have all the infrastructure necessary to test and to deliver signals useful for the development of the lasers for LISA, or test any other equipment that is that requires ultimate frequency stability. So in conclusion, SYLLEX V1 is ready. It consists of two 1064 nanometer lasers, phase locked to each other, power stabilized. They're locked with frequency offsets that you can freely choose, or any frequency modulation, frequency drifts, frequency oscillations, even frequency noise if you want to add it. SYLLEX V2 is currently being developed. It consists of an iodine stabilized telecom laser, frequency tripled, that SYLLEX V1 will be locked to. It's based on existing setups at 1542 and 1544 nanometer, which already meet the LISA specs, so we're quite optimistic of meeting the specs for the SYLLEX V2. It's going to be a fully fibered and monolithic setup with low power, volume and mass, typically in the 10-liter size, 20 watts, maybe a few kilograms. And as I've shown you, Syrte has all in-house facilities for developing such lasers, for testing and validating them. In the longer term, 6 such compact and versatile laser systems will be required for parallel integration of the MOSAs of LISA. Now that's quite an order, so we will collaborate with industrial partners to develop those. But I am very hopeful that within the next year we will have laser sources ready for first tests. And by the time flight models or engineering models of the MOSAs need to be integrated and tested, we have all necessary laser sources available. Thank you for your attention.